All right, so this is as good a time as any to talk about SLP presentations so you can get your minds prepared for this. So presentations are on March 12th, not Matt 12th. March 12th, 3 o'clock in the Digital Lounge, the last Tuesday of the quarter. So we're going to do the presentations differently this time from how they were in fall. Okay? The goal is in part to mimic what's called a poster session. So as you go through your careers, you start writing papers and sending these into conferences, and sometimes a paper will be accepted and you'll stand in front of a group of people and do a presentation with PowerPoint slides or whatever. Sometimes you'll be invited to present what's called a poster. And basically in a poster session you create a poster that describes your work similar to what you do in the SLP, and it gets tacked to the wall and people walk around and they usually eat food and drink wine and look at your poster and read it, and then they talk to you and ask you questions and so on and so forth. And it's a less formal version of a presentation, but it lets more people present their work than having each person come up to the front of the room and talk for 20 minutes. So the SLP presentations are intended to be kind of a model of what a poster session might be like. So the basic setup is you're going to find a table, right? And usually people come in here and they just raid the room and take tables out and put them in the digital lounge or the hallway area. You're going to find a table, put it down somewhere where you want to hang out for a couple of hours. You're going to take your poster and you're going to tape it to the table, right? And if you have any show and tell items, if you've been developing code or making something physical or a circuit or something, you can bring that along also. And basically, you're going to have a little station where people can come over and they can see what you're doing. They can read your poster, look at what you've got to display, and they can ask you questions. You can talk to them about it. And so that's going to be the basic format for this next presentation. It's not going to be a thing where you kind of walk around informally with a poster in your hand and just come up to people and say, hey, what are you doing? Oh, this is what I'm doing. Then you sign each other's sheet and you're done, right? We really want you to get the experience of having people come over and talk to you about your project, ask you questions, make you think about it in different ways, right? And a lot of times you make progress in your project during this type of presentation. You come away with new ideas, or maybe somebody's like, you know, I'm doing something very similar to that. We should compare notes, and maybe you find somebody to collaborate with. Or you get an idea from something somebody else is doing and you decide to take your work in a slightly different direction, right? So the signatures are not the point, okay? The signatures get you a little bit of extra credit. That's just kind of an incentive to make sure that you go around and you talk to other people, because if nobody talks to anybody else, nobody's going to talk to you, right? And you're just standing there for 2 hours. So the signatures are really just a bit of an incentive to make sure that people go out and visit other people's tables, find out what they're doing. But that's not the goal, okay? The goal is really to have people come to your table and look at what you're doing and ask you questions and get into a dialogue about it. Okay, so I put a bunch of words up here about that. But basically, punchlines, you only get your signature sheet signed when you've gone to somebody's table, looked at what they're doing, read their poster, asked them about it, they've told you about their project. When you're done with that, you can hand them your sheet and say, can you sign this, right? You don't sign theirs at that point. You sign theirs when they come to your table and have the same experience, okay? So the goal is not to get the signatures done. The goal is to visit people's tables and have people visit you, right? The signature is just kind of a little bonus you can do. So if you have people that you're working with, you can take turns, right? I can stay here and take care of the table for a few minutes while you go off and visit some other people's tables and so on. If you're working by yourself, you got to sort of split your time. So if there's not a lot of people walking around, right, put something on there, I'll be back in 10 minutes, right, and go walk around and visit some people's tables. And then hopefully you come back to your table and other people will come over and visit yours. So it's kind of a divide your time kind of thing. Does that make sense? All right, so you've still got a few weeks on that, but just wanted to get your minds going in that direction. All right, questions about trees? I'll talk about PA3 tomorrow. But PA3 is graded, and PA3 looked great, so I don't think there was any issues there. If your code didn't work, right, I tried to give you some feedback with suggestions and things to look at or think about. And as always, right, schedule a time to come and talk with me. We can go through your code. Most likely, if your code wasn't working, the right code was probably in there, but there were other things on top of it that might have been, sort of short-circuiting it. So touch base. All right, so tree questions. How many people are coding trees already?
Right?
Yeah.
For the VA4, when I try the symbol, and the symbol is not like trying to balance the tree.
Nope, there's no balancing in this.
Okay.
The only thing you do is analyze your tree and see if it's balanced or not.
Okay.
So, and this has come up a few times actually.
Except when you, in the beginning, start putting numbers that it will balance the tree. That's the only time it will balance, right?
It never does any balancing. The balancing we've been talking about last week, the rotates and all of that, none of that goes into your code. Okay, when you want to insert into a tree, you do exactly one thing. Right, start at the root, and if your number is bigger than the root, come down over here. If your number is bigger than the root, come down over here. If your number is smaller than the root, come down over here. When you're out of nodes, that's where your node goes. And that's got to be where it goes. If it doesn't go there, you're going to lose points. Okay? If you see a really easy way to make it all balanced and nice and full and fluffy, you're going to lose points. Okay? You got to insert using that, and it's got to be a recursive insert algorithm. Yeah?
I know this is a bit early, but would PA5 also be covering trees?
No, PA5 is not going to be trees. So PA5 is going to be what we call dynamic programming. And PA5 will be a group project, so you get to split it up among up to 3 people. All right, so insert, do it recursively. So if I start with an empty tree, it's if I start with an empty tree, it's going to be balanced because null trees are empty. If I put in a 1, that's going to be balanced. If I put in a 2, that's going to be balanced, right? Because what does my tree look like? It looks like this, a 1 followed by a 2.
That's what I meant, like when you try to put the numbers they are on the both sides, it will be always balanced.
Yeah. If I put in a 0 next, that's still going to be balanced because now my tree looks like this. And if I put in a 5, that's going to also turn out to be balanced. And then if I put in a 6, that's going to unbalance it. Okay, and that's exactly what you want because now my tree looks like this. Not quite like that. Like that.
That's a complicated. Quite a few trees.
Yeah, you don't want that stuff going on your trees. That's like a memory leak. All right, make sense? Cool. All right, any questions on rotations that we were doing on Friday? Kind of make sense? So let me...
Can we do like an example of all the nodes in one side? You know what I mean? Like if
It's a good example. So here's a 10. Put in a 20, it goes over there. That's still technically balanced. Put in a 30. Okay, find your balance factors. This is 0, -1, -2. We've got an imbalance. And check your cases. -2 followed by -1, that's a right case. And the way we balance is by basically rotating counterclockwise about that middle node. So basically we bring this 10 down, and we'll end up with this. And that's balanced. Okay, let's keep going on the right. Put in a 40, that's still going to be balanced. One more, put in a 50, that's going to unbalance. Balance factor of 0, -1, -2. And so again, this is unbalanced in the same way, and we need to rotate counterclockwise about the 40. So this will end up changing this 30, 40, 50 into a 40, 30, 50. And the rest of the tree is the same. So that's balanced again. And then put in a 60, and this looks unbalanced to me. So 0, -1, -1, -2. And so this is unbalanced up here at the root. And so now we gotta be a little more careful. So we're still in this right case. So this is node 3. This is node 4. Node 5 will be unchanged, and this is subtree B. Okay, so node 5 is going to stay the same. Its children are going to stay the same. So this is just going to be a 50 with a 60 on the right. Node 4 is going to become the root. So that's going to be a 40. 4's left child is going to be node 3, which is going to be our 20 and our 10. And node 3's right child is going to be B, which was 4's left child, which is the 30. So now your tree looks like this. And that's nicely balanced. And we can add one more. Put in a 70. And now our unbalance is right here at the 50, so we're going to rotate around the 60. And we'll end up with 60, 50, 70, and the rest of the tree is unchanged. And there's like the most balanced tree you could hope for. And so we did a few corrections while we were building the tree, and we ended up with a nice full tree. 3-level, 7 node. So how would we code this? Let's just look at a single rotation. Suppose that we find we're in this right case and we need to turn this tree into that. Okay, node 5, its children don't change. Node 4's right child doesn't change. Node 4's left child becomes this subtree B. 3's left child is the same. 3's right child is going to be B, and 4's left child is going to be 3. So here's what I can do, and I'm not even going to think while I'm doing this. That's the best kind of coding. So I'm starting off with this tree right here. Okay, so node 3 equals, somehow we got to that node, right? That's the place where we had an imbalance of 2 or -2. So I'm going to say node 4 equals node 3 right. Node 5 equals node 4 right. A equals node 3 left. B equals node 4 left. I could do C and D. I'm not going to worry about C and D. What I've done is I've made struct node stars that point to each of these pieces of my tree. And what I want to do is create a tree like this. And so I can do the following. I can say node 4 left equals node 3. And that builds this link right here. Node 3 left is still A, but node 3 right should be B. How do I do that? node 3 right equals B. It's that easy. And since I already set B to be this thing on the left of 4, when I say node 3 right equals B, that takes this subtree and moves it right down there. So I've got that and I've got that, and node 5 is still the same, and node 4 right is still node 5. And assuming that this is supposed to return the root of the new tree, now I just return node 4. And that's the root of the new tree. So all the hard work is figuring out and understanding these rotations, which case you're in, what you want to do to the picture, right? Once you know that, the code kind of falls out automatically. If we're starting from the right-left case, right, what do? Node 3 right equals node 4. Node 4 left equals B. Node 4 right equals C. Right, or you can go directly from here to the balanced case. So this part of the code is really straightforward once you're at peace with what we're trying to do as far as the structure itself. Right, very typical for data structure code. If you understand the structure, right, the code is pretty straightforward to do whatever changes you want to do, and it's even more so in Java. In Java, you can just blink and the code's there. It's amazing. But even in C, it's pretty straightforward. And we'll look at some code for actually doing this at the end of PA4. We'll go through some code because it's actually really beautiful to code this up. Because of the way we do inserts, which are recursively calling insert moving down the tree, if we do this check for imbalance each time that we insert, we'll automatically end up discovering the first place where we have an imbalance. And we do these kinds of corrections, and as we trickle up the rest of the tree, everything's balanced. And it's a few lines of code if you set it up right. So, but we'll do that after PA4 is done. All right, you ready for something new? Let's talk about tries. And these were originally called trees, but it sounds like a tree and it's spelled differently, so they're called tries. It's like a tree, but a lot fluffier. So a trie is not a binary tree. Okay, each node is going to have usually a lot more than just 2 children. And it's not set up like a binary search tree. It's a different goal. But the goal is to say store words and maybe associate some piece of data with them. But let's just store words in this structure. And we want to take a word made up of uppercase letters, so 26 possible letters, and we want to store each word that the user specifies into this structure. And then the goal is to be able to go through this try and say, is this word stored in here? And like I say, usually we'd associate some piece of data with this, but we're just going to store the words and look at how that subsystem works. And it's nominally an order 1 algorithm to store and to retrieve a word in here. It's order n, where n is the length of the longest word you're storing. But most words don't have more than 20 or 30 letters in them. So it's bounded by, say, 30 operations to store or retrieve a word. So it's technically order 1, which is pretty cool. What do you think the penalty is for such great speed efficiency, though?
Accuracy?
Accuracy will not be compromised.
Space efficiency.
Space efficiency. Space will be compromised. Right, this thing is a space hog. But if you really want fast storage and retrieval, this is a way to do it. So here's what a node typically looks like. Node has 26 children, one for each letter of the alphabet. And we're not going to draw our nodes like this because it's going to take forever. So we're just going to kind of draw the things that actually point to something other than null. So we're just going to kind of get a mental picture of what these structures look like. So so let's store the word at. So all of these things are pointing to null except the letter A. The letter A points down to another one of these structures. Let me point to the beginning of it so you don't think it's pointing to A. So the node corresponding to A, this is our root. The node corresponding to A in our root points to another node. And the node corresponding to T in that node, I'm just going to circle it. And by circling it, I'm saying there's a word that ends right here. Okay, so the word AT is stored in this structure. Now, suppose I want to store the word cat. I'm going to take the C, and I'm going to point to another entry. And I'm going to take the word A, and I'm going to point to another entry. And I'm going to circle the word T and the letter T in here. So circle, we're going to set some bit in there. Yeah?
Is it necessary to create a new one each time?
No. So if I already had something that started with C and an A, well, let's do cab. So let's say, okay, so we stored at, and we stored cat, and now I want to store cab. So I'm going to go to letter C, and that's already pointing to a node. So I'm going to go down here, and I'm going to look at the letter A, and that's already pointing to a node. So I'm going to go over here, and I'm going to circle the B, and that says I've got a cab in my structure now. So there I didn't have to actually insert any new nodes. I just changed the bit associated with the B to say there's a word that ends right here. Now if I want to store cats, I can also take this T and have it point to another structure. And there I'm going to circle the S. So now I've got a C, A, T, S in my trie, along with C, A, T, C, A, B, and A, T. So that's the idea. Let me show you a slight variation on this that's a little easier to implement. So our nodes are going to actually have 27 entries. The last entry I'm going to label EOS for end of string. That looks really like fuzzy to me. Yeah, that's a lot better. Okay, the last entry I'm going to label EOS for end of string. So let's store the word at again. Okay, I'm going to take the A, I'm going to point to a new node. And I'm going going to set these end of strings to be 0. And all these nodes are null unless I have something coming off of them. Okay, so I've got an A that points to this node. Here's a T. I'm going to have the T point to another node. And here, end of string, I'm going to set to a 1. Okay, think of it as like the null terminator at the end of a string. This 1 here is telling me that if I start off with an A and then a T, that's a word in my try. So I have one more node I'm pointing to, and I set the end of string, and it means that the way I got to this node represents a valid word in my structure. So now, cat, start off with a C, point to a A, point to a T, and here I set the end of word to be a 1. So C, A, T, and that's a word in my structure. And now if I store cab, C, that's already pointing to a node, A is already pointing to another node, B is pointing to null right now, so I'm going to have B point to another one of these nodes. And I'll put the end of string to a 1 on that.
The last letter only from 1.
So after the B, I got to a node which had end of string set. That means I had a word up to this point, C-A-B. Yeah?
What if for cat you pointed the C to the first A, which was pointing to the next T?
So for cat, I pointed the C to
The A that was for at.
then C, T, A would be a word in my try. So if we want cabs, there's a C, there's an A, there's a B, over here in an S. We'll go down to a new node, and we'll set end of string to be 1 there. Is this making sense? I'm going to have you do this on the board in a minute.
Even if you're looking for another word, then the 1 will not change in this, like the last 2, not the last one. Above.
Say
those
that
one.
again?
You know those ones here, you start looking for caps in the end, right?
Mm-hmm.
Then when you start looking for another word, those ones, they don't change?
They don't change, no.
Okay.
So those are telling me that I have a cab and a cab. Suppose I'm looking for cats. So is cats in here. So I'll start off with a C, that's not null, so I'll follow that to a node. I'll look at A, that's not null, so I know I've got something that starts with a CA. I'll come down here. I'll find a T, that's not null, so I'll come down here. I'll check S, S is null. There's no cats. Right? If there was, S would have to be pointing to something. And if it pointed to something that was at the end of the string, then that would be in there. So what about CA? Is that contained in my structure? Well, if there's a C, it's not null, it points here. There's an A, it's not null, it points here. Is my end of string set? No. So CA is not in my try. Yeah?
So how is this more efficient than just storing strings in it?
Because if my words are only 10 letters long, it takes me at most 10 operations to store or find anything in here. No matter how much stuff I have stored, and I can store 26 to the 10th things in here if I have enough memory. But it's 10 operations to find my word or decide it's not in there. So it's really an order 1 kind of search. A tree would be order log n. So however big 26 to the 10th is, it's still fairly expensive. And traversing this is really fun because it's like super recursive, right? Print out the letter A and then followed by every word that you find by traversing a trie where this is the root, right? You know, there's at least one thing. Print out the letter C followed by everything you find by traversing a trie where this is the root down here, and so on. So that's just like a bunch of recursion. And your recursion ends when you get to an end of string equal to 1. That ends a word, and when there's nothing in here pointing to anything, you know that there's no other words that began with everything that got you down to there. Deletion is tricky. Deletion is not efficient. So we can delete a word by just changing this end of string. Right, so suppose we want to delete, well, let's go ahead and put CA in. So C is here, A is right here, that points down here. If I set that end of string to a 1, now I've got CA stored. Okay, if I want to delete CA, I can take C, follow it down here, there's an A, come down here, just change that to a 0 again. CA is gone from my trie. But I haven't disturbed the fact that I could be following from CA down to a B for cab, or down to a T for cat. But if you delete a lot of stuff from a trie, you can end up with nodes that that point to stuff and end up not pointing to anything, with just basically wasted memory, right? So deletion's not super efficient. I'm going to let you ponder that for a while. We'll do these on the board tomorrow. These were explored, among other things, by someone named Fredkin. He was, I believe, an IBM fellow. I don't know if he was at the time. But he explored these, and I think he coined the name trie, which are supposed to be an abbreviation of, I think, tree retrieval. So that was the RIE part in trie. Because it was an efficient way to pull data out from this structure. And one of the kind of weird things about tries, so we've got this word cabs stored in our structure. There's nowhere in here that there's a string containing CABS, right? That's not actually stored anywhere. It's sort of in the pattern of links that lead you to a particular end of string marker. Somewhere buried in that collection of links is the fact that the string cabs is stored in the structure. But it's not explicitly stored anywhere. And every other structure that we've dealt with, hashes, trees, arrays, lists, right, our data is actually stored explicitly somewhere in memory. There's nowhere in memory where we're going to find a C followed by an A and a B and an S. Right? It's sort of an artifact of how we follow these links. And so that's a little quirky. But that was Fredkin. So let me do a sidebar here. Not on the test, but it's something you should hear about at some point anyway. And since we're talking about Fredkin, this is an opportune moment. How many people here have heard of reversible computing? All right, we'll have fun with this. So I think this is probably the thing Fredkin is known for most. So IBM used to be this hotbed of research. I guess they still are in some ways. But they had these people called IBM fellows. You could get a position there, and basically you got paid to come in and think. It's like a really cool job. And Fredkin was one of these. And what Fredkin was thinking about was the cost of computing. Computers were getting smaller and smaller. This was like in the 60s, I believe. Computers were getting smaller, and as computers get smaller, they tend to get faster, right? Because the distance that signals have to travel decreases. They also tend to run hotter because you have more stuff in a small amount of space, and that stuff, transistors, wires, produces heat. And if you have a certain amount of heat in a small area, right, it's harder for that heat to dissipate. And so devices were starting to run hotter and hotter, and it's a problem today. It's why we have fans in our computers, right? It's why all these things make noise, because we got to move the hot air away so that new air can get heated up to take the heat away from the components. Now we can do things to make components use less power. So if you go back to 250, we talk about different kinds of transistors, and maybe you talked about this. NMOS transistors are very power hungry. CMOS is very energy efficient. Something called ECL, which isn't used much anymore, is really, really power hungry, but super fast. So it's what some of the old supercomputers were made from. But you turn it on and the lights in the city dim, you know. And all of that power generates heat, right? That's what it translates into. So Fredkin was looking at this question of how much power do we need to do calculations. And if you go beyond the physics, beyond the fact that moving electrons through a wire involves resistance, and you know voltage times current is power, and that's watts, and that's heat, right? If you go beyond all of that and you imagine a world where there's no resistance in your wires, right, and your power dissipation is zero, due to those kinds of effects, and you take something like Z equals X plus Y, and the circuitry in your computer is performing this calculation. It's taking two numbers, X and Y, and setting Z equal to it, and then it returns Z to whoever called this function. Well, here's the weird thing. When we take X and Y and we add them together, and we know there's some Z, and we get rid of X and Y, right, we throw them back into the memory pool or we reuse them, we generate a little bit of heat. We generate heat because we have destroyed information. Now, if you know that X equals 10 and Y equals 5, and we add them together, Z is equal to 15, we haven't lost any information yet. But if I do something like X equals X plus Y, so X is 10, Y is 5, now I set X equal to 15, I've lost the fact, well, I haven't actually lost it here. I've lost the fact in some sense that X was originally equal to 10, right? Or when you return and you return the sum, but you've lost X and Y, information has been destroyed. And Fredkin's analysis was that destroying information generates heat. And so here's the quintessential information loss. Here's an AND gate. And you've got an X and a Y going in, and you've got a Z coming out. And suppose your output here is a 0. Well, it's possible that your inputs were 0, 0, or 0, 1, or 1, 0. Right? The only thing you know is that they could not have both been 1 because your output would have been a 1. But if you don't somehow save the values of these inputs, that information is lost and you generate a little bit of heat. And he calculated how much heat is generated when you lose information. And it's not 0. It's a very small positive amount. And the idea is, yeah, it's a really small amount of heat, but if you had a gazillion of these gates operating and each one was losing, you know, a femtowatt of information, so generating, I don't know, 10 to the minus 15th watts of heat. But you've got 10 to the 18th of these things, that's 1,000 watts, right? And you can't make your wires more efficient. This is assuming there's no resistance, there's no heat loss due to those kinds of physical effects. This is just from the destruction of information. And it's a fundamental limit. And as you scale up to the point where we're getting Avogadro scale machines where you have, say, 10 to the 23rd transistors in a little bottle of computer, these small pieces of heat that are generated overwhelm your system. So he invented what is called a reversible gate. And it's basically a gate that has multiple outputs. It's like an AND gate, but it has multiple outputs. And by saving not just the actual result of the AND operation, but also these auxiliary outputs, you don't lose information. You can reproduce what the original inputs were. And so his idea was to build computers out of these reversible gates and eliminate this information destruction generated heat. So this is a thing. Yeah.
Should that be way harder than originally is?
Yeah.
Like we know 2 is equal to 2 equal to 0 plus 2 or 1 plus 1.
Yeah, yeah.
So it's much harder than just say 1 plus 1 equals 2.
Yes, yes, definitely. But this is the term reversible, right? So x plus y gets you the number 2. In a non-reversible computer, we can't go backwards. We can't run our calculations in reverse. We can't say, okay, my final answer was 2. Let's go back one step. What were x and y? We've lost information. Was it 1 and 1, 0 and 2? Was it a million and negative 999,998, right? So if you can preserve all these pieces of information, then you can run your calculation backwards. So if you've done thermodynamics in physics yet, have you done that? Okay, so like entropy and laws that entropy always increases and things like that, they tie into this also. And why some operations are reversible and some are not, right? In particular, the ones that generate entropy, I think, are not reversible.
Well, even this theory of conservation of information is the single most, it's even more powerful than things like conservation of energy or any other conservation law when you deal with high-level physics involving universal field theory, like quantum mechanics and everything. The only tangible progress since Feynman has been using basically conservation of information.
Yeah, yeah. So this gets into the weird stuff really quickly. And it's not something that affects us as macro scale programmers, but if you end up in areas like architecture, especially nanoscale or femtoscale architectures, these are issues down the road that are going to be things to deal with. And it's a lot of theoretical stuff. How important is this today? Probably not. But down the road, it's another thing that's going to have to be dealt with. So you can Google reversible computing or Fredkin gates, and there's a few others. I'll misspell this, but something like that. Well, let's just. Google knows. Maybe Google knows.
Google knows, but you cannot reach Google.
Yes, Google denies me. Resolving host, that's nice. That's progress. Well, Fredkin will get you there, but I think Tofeli's the other one.
But that changes the architecture, like the thought experiment of a computer using reversible gates kind of changes the hardware limitation from processing and more hard memory, right?
Right.
Now memory is the limiting factor more than anything else.
Yeah, yeah.
But that's useful to us today now, right? Because now we're getting this end of like capability of these two-dimensional chips. So
yeah, we've been there for a while, but we keep going on the same path anyway.
We can store like almost, what is it, don't we have like SD cards capable of almost 1 terabyte now? So
Oh yeah, yeah.
what, isn't it almost to the tipping point where like throwing in a bunch of reversible chips and
Could make sense.
sacrificing more memory wouldn't actually be that costly anymore, right?
Yeah, and we're always looking for what to do with more transistors. So I don't think anybody's doing this commercially yet, but it wouldn't surprise me if that wasn't too far down the road.
I'm sure you do other weird stuff like not all output of a reversible gate is now stored kind of useless knowledge, because if you do a similar calculation that uses the same number of a reverse output gate and you use
Right.
that in a different gate, you still don't lose the original input.
Right,
So
right.
you can use the same bit of memory for multiple things.
Yeah.
Even though it's hard stored, not
So-
random.
And the other question is, if everything you do is reversible, is there really a point in doing it at all?
Yeah, is
Right?
that really
Or are we really just kind of restructuring information as opposed to actually synthesizing new facts or concepts? So, all right, so that's a good stopping point. So do some Googling on that. We'll go back to tries tomorrow.